Hi, Kelvin here. In this video, we are going to consider a propped cantilever beam. And I will show you how to draw the reaction forces, the shear force diagram, and the bending moment diagram. Consider this stadium. This beam is not supported anywhere along this length. Also, consider this beam element. These beams, none is supported along this length. However, here you can see that this beam is supported before the end of the cantilever. This diving board supposed to be a cantilever from here. However, it is supported here. Hence, this beam is propped. This beam is not propped. This is a cantilever. In building structures, some cantilevers are not supported. In this question, this beam is a cantilever, considering it from here. However, along the span of 4 meters, it is supported. Hence, this is a propped cantilever beam. To solve this problem, the first step is we're going to find the reaction forces at this point, A and C. This is pinned, while this is a roller support. When we get the values of the reaction forces, we're going to substitute back to this question, and we're going to draw the shear force diagram. The shear force values will help us to draw the bending moment diagram. Let's get started. Step number 1. We're going to draw the free body diagram for this question. That is, we're going to repeat this question and we're going to change the support with an arrow. For a pinned support, we're going to have 1, 2. And for a roller, we're going to have just only 1 arrow. For this point A, we're going to have V subscript A. And for the horizontal force, we're going to have H subscript A. At point C, we're going to have V subscript C. With this, we can now move to step number 2. In step number 2, we're going to have that forces going up must be equal to the forces coming down the beam. The forces going up is V subscript A and V subscript C, while the forces coming down is 40 and 20. You can see that V subscript A plus V subscript C will give us 60 kilonewton. Next, step number 3. Forces to the right is equal to forces to the left. The force going to the right is H subscript A, and no force is coming to the left, it is 0. We have found the value for our first reaction. Next, step number 4. Summation of all the moments at any point. Now let us choose at point A is 0. This means that clockwise moment is equal to anti-clockwise moment. At this point, all the forces acting here is 0. Hence, we are left with 1, 2, 3 reaction forces. Next, we are going to consider each of these forces one by one. Let me start with 40 kilonewton. I will assume that these two do not exist. 40 will push this beam to turn in the clockwise direction. Hence, I'm going to have 40 multiply the distance perpendicularly to the point where we are taking moment from is 2. Moment is force multiplied by the perpendicular distance. It must be perpendicular, that is 90 degrees. We are done with 40. Next, let's consider 20. I will now assume that this both does not exist. 20 will turn this beam to turn in the clockwise direction. I will have 20 multiply the distance from 20 to the point where we are taking moment from is 6. Hence, I will write 6. Next, let me consider this. V subscript C, in the absence of these two forces, will turn this beam anti-clockwise. Hence, it will move to this section, which is V subscript C multiply the perpendicular distance is 4. We're going to look for the value of V subscript C. This is 80 and this is 120. On this side, I will leave V subscript C. This will move over to divide everything here, and we are going to have that V subscript C is 50 kilonewton. Now we have the value of the second reaction. Next, step 5. In step 5, we are going to substitute. We are going to substitute the value of VC into step number 2. And we are going to find the value of our V subscript A. Our V subscript A is going to be 60 minus 50, which is 10 kilonewton. We have found the value of our last reaction. Now, with these reaction forces, which is this, and this, we have actually completed everything we are looking for. Next, we are going to draw our shear force diagram. That means we are going to redraw this and change the values. Draw a line under and begin to draw our diagram. Next, instead of this, we now have this. By replacing the values of the reaction forces, H subscript A is 0. Hence, I will ignore it. Next, we are going to draw a line. Next, I will draw a line for the shear force diagram. I will draw another line for the bending moment diagram. This is for the shear force diagram, and this is for the bending moment diagram. Next, I will identify my points. This is B, here will be B. This is C, here will be C. This is D, and here will be D. Here is A, and here is A. This line is the 0 line for the shear force, and this is the 0 line for the bending moment diagram. Considering the shear force diagram, any value up is positive, any value below the 0 is negative. And for the bending moment diagram, any value up is positive and any value down is negative. Next, for the shear force diagram, we don't have any uniformly distributed load. Hence, from 0, 10 will move up. Between A and B, there is no load. Hence, we're going to have a straight line. At point B, there is a 40 kilonewton. This is 10. it will push it down 10 and push it down by 30. Hence, this is not a graph and this is not to scale. So I will assume this point to be minus 30. Remember, this is 10 and this is 30. But because it fell on this side, I will give it a minus. Next, between B and C, there is no load. Hence, I will draw a straight line to point C. This line is on the 30 line. Next, at point C, there is a 50 kilonewton. It will push it up by 30 and push it up again by 20. It's going to go a bit above this 10 because this point is 20. Next, at point C to D, there is no load. Hence, I will draw a straight line. And at point D, it's going to come down to 0. This is our shear force diagram. Here is positive, here is negative, here is positive. Next, before we draw the bending moment diagram, there are two methods that we can use to draw our bending moment diagram. One is by using the mathematical method. The mathematical method is by cutting this beam at different points. That is, I will cut the beam at point B to obtain the value of my moment. And I will equally cut this beam again at point C to know the value of my moment. Bending moment at the end of a beam is 0. Bending moment is maximum at the mid span of the beam. Shear force is maximum at the support. In this video, I'm going to use the second method, which is the graphical method. The graphical method is finding the area of the shear force. The area under the shear force will help us to get the shape of our bending moment diagram. The area here is 10 multiplied by 2. This is 20 kilonewton meters. This is meter, this is kilonewton. Next, here is, this is 2 meters and this is 30. Hence, here we're going to have 60 kilonewton meters. However, this is on the negative side, so this will be a minus. For this length is 2 meters and this is 20. Here is 40 kilonewton meters. Next, at the support, bending moment is 0. This gave us 20 kilonewton meters. Let's assume that 20 kilonewton meters is here. Next, this gave us minus 60. 20 we add to this. However, this got a minus, so it's going to be 20 minus 60 and we're going to get minus 40. Look at the negative part. Hence, I will come down to look for 40 and it's going to be a minus. Next, minus 40 we add to the next one. However, this is minus 40 and this is plus 40 and we are going to end up with 0. Remember, our value here is 20, our value here is minus 40 and our value here is 0. Next, we are going to join all the points. Here we wouldn't have a parabola because there is no uniformly distributed load. With a straight line, I will join this, then I will join this, then it's going to end here. This is the positive part of the bending moment diagram, and this is the negative part of the bending moment diagram. The point where the bending moment diagram cuts the zero line, this point is known as point of contraflexure. We can also call it point of inflexion. How do we calculate for this point? To calculate for this point, we are going to find the moment at this point. Between B and C is 2 meters. That means here, if we call here x, this remaining point will be 2 minus x. How do we find this distance? To find the point of contraflexure, we are going to take moment about this point. If we take moment about this point, this is moving clockwise, because we are going to have that clockwise is equal to anti-clockwise moment. If we have that clockwise moment is equal to anti-clockwise moment, hence we are going to have 10 multiplied by this distance will give us 2 plus x. This we turn this in the anti-clockwise direction. We are going to have 40 multiplied by x. We just took moment about this point. 10 times this will give you 20, plus 10 times this will give you 10x is equal to 40x. This will move across. We are going to have 20 is 40x minus 10x, and 20 will give us 30x. Here we are going to have 20 divided by 30 is x, and you see that your x is 2 over 3 and your x is 0.67 meters. If here x is 0.67 meters, then this remaining part will give us 1.33 meters. Remember that this side is 2 meters. Hence, from point A to this very point of contraflexure is 2.67. If you find this video helpful, feel free to click the like button. Also, subscribe for more videos like this. I will see you in the next video lesson.